Find out what the rover's up to as it drives around the red planet, tests its instruments, and takes some more pictures. We've got 3 speakers today, and then we'll take reporter Q&A. You can follow along with the visuals for this news telecon at http://go.nasa.gov/curiositytelecon. go.nasa.gov/curiositytelecon. Okay, our speakers are going to be Richard Cook, and he's the Mars Science Laboratory Curiosity Project Manager with JPL. And we have John Grotzinger, the mission's project scientist with the California Institute of Technology in Pasadena. And we have Mark Lemon of Texas A&M University in College Station, and he's a co-investigator on the Mars Science Lab Curiosity Science team. We're going to start things off with Richard Cook.
So good morning, everybody. Thank you, Jane. I just wanted to go on the telecon today to give you guys a brief update on what the rover's been up to. Curiosity, I think, everyone knows, remains in good shape and good health. It's operating on the surface of Mars now for about 6 weeks, 43 sols, and we're obviously in the process of planning what to do on Sol 44 at this point, but we are giving you an update on what we've been doing over the last few days, and John will talk, and Mark will talk a little bit more about what the plans are coming up over the next short period of time. But if we go to chart number labeled Grotzinger number 1, you can actually see a map of a picture taken from the HiRISE spacecraft, over which we have superimposed the track that Curiosity has followed from the Bradbury landing site as we go towards the Glenelg target, and John will talk some more about that in a bit. The white track you see there is the rover's progress over the last few weeks. And again, last night we drove for another 30 meters to get to a now total drive distance from the landing spot of 289 meters or 950 feet. So we are making slow and steady progress over to Glenelg. We're actually more than halfway there, but important, as you know, we've been stopping periodically to do various activities, including last week finishing the characterization phase of the project. We're now at a point where we want to start doing some surface contact science, and so the team has been looking for a interesting target to stop at and to start to use the MAHLI and APXS instruments on a Mars rock. And if we go to the next chart, we can show you the target that we've now picked out. This is the Grotzinger 2 image. That is the rock you see there in the lower center. We have chosen to name this rock because it is the first place where we're going to do a sort of complex set of arm operations to do up close science on Mars. We've chosen to name this rock target Jake Matijevich. And for those of you who I think a lot of people probably know who Jake was, but was a very instrumental rover engineer, worked on a number of projects, including led the Sojourner rover team, worked on Spirit and Opportunity for a number of years, and has worked on MSL as well for a number of years. Unfortunately, he passed away right after landing, a few days after we landed on the surface. And so as a way to honor him and his contributions to the Mars program and to MSL in particular, we decided to name the first rock we were going to do contact science on after him. And so we've now managed to find that rock, and so it's now been labeled Target Jake Matijevich. So with that, I think I'll pass it on to John to tell you why we are interested in that particular rock, as well as what we plan to do after this.
Great. Thanks very much, Richard. So with the rock now called Jake Matijevich, the science team has had the interest for some time now, as we're driving across the plains, to find a rock that looks like it's relatively uniform in composition, to do some experiments between ChemCam, which we've been acquiring a lot of data with, and APXS, which we haven't used yet on a rock. Both of those instruments are capable of measuring the chemistry. ChemCam, as you know, acquires data at a very small scale of spatial resolution, less than 1 millimeter. APXS, on the other hand, integrates over a much larger area, approximately 1.5 centimeters in diameter. And so both of those instruments could make a measurement, and there could be differences between the measurements because one is measuring at a small scale and one is measuring at a larger scale. So these rocks that we drive by on the plains here that look dark, we assume that they probably have basaltic composition, and so it's a familiar material to us. It's actually the calibration target for the APXS instrument. So the hope is that we can analyze this rock and then do a cross comparison between the two instruments. Not to mention, it's just a cool-looking rock there, sitting out on the plains with almost pyramidal geometry, so that's kind of fun as well. Okay, if we flip ahead then to the next slide, what's called Grotzinger 3 here, we see an overview looking in our drive direction towards the Glenelg area. And remember, Glenelg was sort of selected because it represents the intersection of three relatively different terrain types coming together. And now we're sort of looking into that area where they come together. So Glenelg really isn't a point. I think many of you will ask, when will we get to Glenelg? And we don't actually have a point defined because it represents kind of an area. But we reckon we're about 200 meters away from that area where we'll start finding interesting things. So indeed, we really do think it's going to be interesting. If you go ahead to the next one, Grotzinger 4, I guess it would be, there you can see a light tone unit, which we believe to be the material that from orbit has this signature, this property of having relatively high thermal inertia as compared to other materials around us. And again, just to remind folks, that's the ability of a material to retain its heat. So late in the day or at night, orbiters are able to observe this rock differentially well because it seems to be giving off heat late into the day and into the night. So we don't know what the reason for that is, but it's always been a bit of a beacon for us, and we're getting closer and closer to it. The neat thing that we're now seeing are features that we really didn't recognize from orbit before, which are relatively thin bands of a darker rock that may somehow be interbedded with this light tone unit. We don't really know much about the geometry at this point from a distance, but we just wanted to give you a flavor of the kinds of things that the science team observes when the data comes down, and that gives us some interesting discussion. And so we see these dark bands. We don't really know what they are, but they're obviously very discrete. They also seem to form layers, and those layers may be interbedded with thicker layers made out of the light tone materials. So as we get closer into the Glenelg area, we'll understand better and better what these are. But that gives you a sense for what we're seeing and the direction we're headed in. And with that, I'm going to turn it over to Mark.
Okay, I will change the subject a little bit from looking down at these rocks to looking back up into things orbiting around Mars. Just to remind you, Mars has two moons, Phobos and Deimos. They're both very small. They're around 10 miles across, give or take. Phobos being a little bit larger, Deimos smaller. They are fast. They're closer to Mars than our moon is to Earth. Phobos goes around Mars in less than 8 hours. Deimos takes around 30 hours, which is a little bit more than a Martian day by a few hours. As a result, on Mars, we see that the sun rises in the east and sets in the west, as we're familiar with. Deimos does the same thing, but it goes very slowly. It spends 2.5 days in the sky and then 2.5 days down. Phobos goes the other way around. It takes 4 hours going across the sky from rise to set, but coming up in the west, going down in the east. On Sol 37, we got to a point where these objects start to cross paths. Phobos grazed the edge of the sun, as seen from Curiosity, and we took a lot of pictures. So I want to talk today about what pictures we took and why we did what we did. So we had what's basically a partial eclipse of the sun, Phobos being in front of the sun, as seen from the rover. Would have been an annular eclipse, with Phobos entirely in the middle of the sun if we were way up at the top of Mount Sharp. So if you look at the first graphic, Lemon 1, that's got a comparison of a couple of the images that we got from this sequence. We used MastCam, which has two what we call neutral density filters. They're similar to using eclipse glasses here on Earth, so we can look directly at the sun when those are in place, but not when they are not. On the left, you see our left camera, which has lower resolution, but can take video a little bit faster. And on the right, you see the higher resolution Mastcam 100 image. Those are taken at two slightly different times, 18 seconds apart, so you can see Phobos' motion across the sun in that. If you go to Lemon 2, you will see an animation from the M100 images of the frames that we have on the ground so far. Now, we actually took 256 images with the right eye at high resolution and 384 with the left. Of those, only about 40 right and 60 left actually show part of this event, and only a small subset of those are down on Earth right now. You're seeing the M100. If you follow the link in the caption, you can see the M34 as well. The Mastcam has a video mode which was used for this acquisition, which gave us 2 frames per second for the right eye, 3 frames per second for the left eye. For comparison, we've done this with other rovers, and in fact, the Opportunity rover is in the middle of doing this right now. For that, it's something like 1 frame every 3 to 10 seconds. So we're doing this much faster and at higher spatial resolution, as you see in the animation on the page. So why do we take all of these images of these 2 little moons crossing in front of the sun? Well, one thing is that they have tidal forces that they exert on Mars. They change Mars's shape ever so slightly. And that, in turn, changes the moon's orbit. Phobos is slowing down. Deimos is speeding up like our moon is. This is something that happens very slowly over time. Phobos will eventually break up and fall into Mars. And with the transits, we can measure their orbits very precisely and figure out how fast they are doing this. The reason that's interesting is it constrains Mars's interior structure. We can't go inside Mars, so we can use these to tell how much Mars deforms when the moons go by. So we measure the transits very precisely. We get information about Mars's interior structure. We think the precision of these measurements with the high time resolution and the high spatial resolution with M100 will also tell us something about Phobos' insides and whether it is uniformly dense or whether there are variations. Now, just to close, I want to tell you that a few days later, Sol 42, we started this process again. There were 2 more transits. We do not have any full-frame products on the ground, but we do know that we successfully acquired them. This was interesting because Phobos set in front of the sun minutes after it rose over the crater rim. So we got a picture of the sunrise partial eclipse. This was really cool because a few months ago here on Earth, I took my daughter out to see a sunset partial eclipse on Earth. So I can't wait to show pictures of this from Mars as well. From that one, we got 240 images in each eye. It was a bit slower. Then later that day, the moon Deimos the sun passed behind Deimos as seen in the sky. Deimos was almost stationary. This is what we call in astronomy a transit, kind of like the transit of Venus. And we get the timing from that as well. We took over 1,000 images of that event. Something like 100 in each eye probably showed the event. One of the reasons that we took so many images is this is basically a really hard thing to do. The timing is very precise, and we need to make sure that the event is in the images. So we take a lot and try and get the actual event to happen in the middle, which we succeeded in doing all 3 times. So over the course of time, we'll be looking at the thumbnail products that we have down. We'll be picking the best and bringing these full-frame images down. I think we'll have some cool products to go beyond what we can show now, but we'll have to be patient. It takes time to get this data down from Mars, especially when there's so much cool stuff going on with moving the rover around and getting those images on the ground. Jane.
Okay, thank you very much. We'll begin our Q&A session with reporters who are on the line. And if you do have a question, again, a reminder to press *1 so we can put you in the queue. Our first question today will come from Seth Borenstein of Associated Press.
Yes, thank you very much for doing this. I guess this is for Mark. A couple quick things. First, and a follow-up, have we ever gotten pictures of an eclipse from Mars before? Have any of the past rovers done that or just never really looked up at the right time? And how often do we, with 2 moons, you described essentially 3 eclipses in 5 days, I think. So how often do you get eclipses there compared to like here, where it's it's an unusual event?
Okay, with the first question, as far back as the Viking landers, they observed the ground to get darker when a transit was happening, but they don't have pictures of the transit itself. With the Mars exploration rovers, we've been taking such images since March of 2004 and getting them, and Opportunity just successfully acquired some over the weekend, and I believe they are considering a couple more opportunities today. So yes, we've got them from some previous rovers. The advantage that we have from this rover is the much faster imaging capability and the higher resolution. So I think we're going to have some great products, and we're going to have some better ability to constrain Mars's interior because of these advantages. Second question was, how often does something like this happen? This is basically a sit around for a long time with nothing to do with respect to this, and then hurry up and do quite a lot. There are specific, what we call transit seasons on Mars, that the shadows of the moon work their way north to south, south to north across the planet every Martian year. So twice every Martian year, the shadows pass over you. We're close to the equator, so that means that the Phobos and Deimos shadows pass over us relatively close together, and Opportunity and Curiosity are at similar latitudes. So Curiosity got the first set of 3 by a couple days, and then Opportunity had a set of a few immediately after that. The next set is something like 11 months from now.
All right, the next question will come from Joe Palca at NPR.
Hi, thanks. Got a couple questions about the rock that you're going to be using for your first arm testing. First of all, I wonder if you can tell me its size approximately. Second of all, do I see it in Grotzinger 4? Is it at the bottom of that picture? Is that what we're looking at? And the third thing is, you guys said Jake Matijevich's name in 2 different ways, and since I have to say it on the radio, I'd like to know which one to use.
Richard, why don't you take the last one while I figure out the first one?
Okay, it's Jake Matijevic.
Okay, that's what I'll use.
Okay. And John is looking at the picture.
Okay, maybe you could tell me a little bit about the movements of the arm that you're planning to use while he's looking for the size issues. I mean, what kinds of things just come up close to it and place the arm on it as close as you need to?
Yeah, it's actually a fairly complicated set of measurements, and John can add some more detail to it, but we're actually going to drive up to it, use the APXS to do an elemental composition measurement against it. I think we're then actually going to back up and do ChemCam observations on it, and then have to reapproach it and do some imaging close up with Molly. And so it's going to be a set of actually tied together both arm and rover motions as well.
Thank you.
Takes 3 or 4 days, I believe.
Thank you. And the next question is Pete.
Wait a minute. John still has a question.
Yeah.
Oh, I'm so sorry. I'm
Right.
moving along too quickly.
So I don't believe that that rock is visible within the view that we've got here, but don't quote me on that because I'd actually have to go back and check it quantitatively. And the interesting, just to add a little bit about it, so I mentioned before why we want to do the coordinated measurement between APXS and ChemCam. The interesting challenge for us in terms of the distance is that we approached this, and it was a very, very successful drive. We came up to within 2.5 meters, and the uncertainty in a drive of this type always largely resides within how much wheel slip there is. And the RPs the rover planners make a prediction of that in advance, and then you see what the actual is once you've completed the drive. So they did real well and came up so that basically tomorrow, or now as the science team likes to say, Solaro, we will just need to do a short bump to get into place to actually get to this, and we're pretty optimistic about that. Depending on exactly how far away we are from the rock, will determine whether or not, in order to use ChemCam, we have to back off, or whether or not we can stay in the same place, which would save us all en route to our drive. So there are issues of geometry and what the actual position of the rover is, and our flight rules for how we use ChemCam that determine that are a function of our known distance away from the rock. So it's complex, and that all that activity and all those considerations is really what honors Jake Matejevich so well.
Size?
Okay, now we go to Pete Spotts at the Christian Science Monitor.
Oh, thanks. One for John and one for Mark, if I may. John, quickly, is there anything about the shape of that rock, the way it's been sort of cleaved, that might suggest something beyond basalt, or is that just what basalts can look like once they've been busted up a bit? And for Mark, I wonder if you could unpack a little bit how you take this information about Phobos and its shrinking orbit, if you will, and tease out of that information about Mars's interior.
Yeah, I would guess to answer the first part, the shape of that rock is actually, for those of us that worked on Mars Exploration Rover, if you're aware of that mission, the very first rock that we analyzed on that mission with the Spirit rover is a rock called Adirondack, which is another rock that has a somewhat pyramidal looking shape to it. And so when you use the term cleave, one of the questions that we ask associated with the morphology of the rock is to what extent the shape of the rock reflects the impact of processes that are active on the surface of the planet today, most prominently wind, and is there something about changing wind directions that results in a sculpting of a rock that has that shape? But it is also important to keep in mind that the shape of any given rock that's lying around on the surface may reflect the patterns by which the rock was broken from a much more extensive volume of rock, and the intersection of those fractures may set the pattern of the rock initially before it begins the wind sculpting process. So in this case, we really don't know. We're going to image it and try to get some data that will help us address that question.
Okay, and this is Mark. So the question to me is, how do we go from a nice picture of this partial eclipse to knowing something about Mars's interior? And I'll say, first of all, that my expertise in my job is to make sure that we get really good pictures, even under the challenging circumstances of pointing and timing these things. And then second, what we actually need out of the picture is a precise determination of where Phobos was at a particular time. If we take a picture of Phobos, say, at night, then you get a position of it in the sky, but there's some uncertainty in the position. Having things like stars in the image would help. This is something that we've done with Spirit, but not with Curiosity so far. The sun makes a great target here. We see Phobos. We get, in particular, the instant when Phobos first encounters the sun and the geometry where it's at the maximum point, and then the instant where it last encounters the sun. And those constrain exactly where Phobos is in its orbit very, very well. And then people who are off of the team whose expertise is in generating an ephemeris, is in knowing where things in the solar system are at any given time, use that information to figure out how Phobos's orbit has changed from, say, 2005 or the 1970s to now. And then people whose expertise is in understanding tidal forces look at that and try and figure out how much of a tidal bulge, that it actually deforms the rocks on Mars slightly, how much that happens, and therefore how deformable Mars's interior really is. So it's a multi-step process, and it starts with the great pictures, but eventually these images will be available outside the science team to the people whose expertise goes into these other areas.
Okay, we have quite a few people in the queue waiting to ask questions, so we'll try to get to all of you today. And I did want to ask the callers, please, the reporters who are asking questions, if you can speak right into the phone to make sure that all of us can hear you clearly. We're going to take the next question from Kip Stoltz of the Ventura County Star.
Hi, thank you. My question is, speaking a little more broadly, is one of the objectives of this mission to assess an idea from a JPL geologist named Tim Parker that of a northern ocean may have existed on Mars a few billion years ago?
I'll take a swipe at that one. I guess, what we're trying to do with Curiosity is just understand first and foremost, the local environment that we landed in here. And then as we get some measurements under our belts about what we see in the landing ellipse, to then eventually head on to Mount Sharp and see what's there. It's just going to be difficult to address a much broader hypothesis about whether or not there was a global ocean on Mars.
All right, the next question is from Reuters' Irene Klotz.
Thanks very much. I have a couple of quick clarifications for John first. Did you say that you were going to reach the Jake Rock tomorrow, as in Thursday?
Right. No, it won't. Actually, it won't be tomorrow because what we have going on in the planning of the current SOL is a very, very restricted plan, because for the first time, because of latency and data coming back from the UHF passes, instead of working a 16-hour SOL, we're going to work a 12-hour SOL. And that restricts our ability to actually do that bump drive, and instead we're going to do some other activities with the arm to get warmed up for what we're going to be doing on the rock itself. So it will actually be the SOL after tomorrow.
Okay, thanks. And John, do you have just some rough estimate of the height of the rock and the width at the base? And then I have two questions for Richard.
Yes, Irene. That information. Sorry, somebody asked me that before. That's all printed in the press caption. The rock is about 25 centimeters tall and about 40 centimeters wide at the base there in the view angle that we see.
Thanks. And let's see. I had Richard. I wanted to ask you just something about this sequestration. If that has any impact at all on this Mars mission, if that comes to pass, and also if you or John have any information on the SAM's atmospheric sampling. Thanks.
So to be honest, the sequestration, we really haven't had a conversation with NASA headquarters about that as to what impact it might or might not have. We have a funding profile for both this year and next that we've agreed, that has been previously agreed to, and so the project is working with the understanding that that's the funding that we'll get for this year and next. And so it's really something that you'd have to ask them, what the headquarters, what broader impact it might have. And then you asked about SAM. Do you want to answer?
The atmospheric sampling. Thanks.
Yeah, so we are in the process of using the SAM instrument, the tunable laser spectrometer, as well as the quadrupole. Have both made measurements. This is the kind of process where we need to do this over and over and over again to be sure about what we're seeing. So the team is working on that, and we'll keep you updated as we feel confident.
Okay, the next question comes from Alan Boyle at NBC News.
Thank you. I remember Joy Chris was discussing what the characterization of the terrain was and how she wasn't willing to stick her neck out. Is anybody willing to stick a neck out further and talk about what you've been finding so far in terms of characterization of the terrain?
In terms of what's around us, we're driving across a largely soil-covered surface. There have been a few exposures of what the team considers to be bedrock that we've encountered as we've driven along. We actually think the first sample of that bedrock occurred at the target we labeled Goulburn, which was one of the excavations created by the thruster impingement during landing. And so we're getting a set of observations, and we're working on those. And we hope to have a story out on that for you all probably sometime next week.
Next, we'll take a question from Emily Lakdawala with the Planetary Society.
Okay, I'm wondering if you're going to be doing anything besides APXS and MOLLE on this Jake Matijevic rock, if you're going to be using the brush at all. I assume you're not going to be using the drill or other sampling tools yet, and if so, I'm wondering what the plans are for the use of those, whether you're still planning on using them before you get to Glen Elg, or if you're going to wait till you get to that area to start.
Yeah, Emily, I think we're not able to use the brush right now because we're still doing some testing and final qualification for that. And obviously that depends on getting to know the terrain and what it is that we're going to be brushing. So right for now, it's going to be APXS and ChemCam, remote sensing, and then MOLLE observations. That'll be pretty much it. Sorry, I didn't answer the rest of the part. So as we go to Glen Elg, the next thing in our sort of prioritized list that gets us towards the process of being able to use SAM and ChemMin is to try to find some type of fine-grained deposit, I would guess some kind of aeolian bed form, that we'll be able to scoop up and then process that in Chimera and begin to understand that mechanism and hopefully even dump some of that material into SAM and ChemMin. That may occur before we get to Glen Elg if we find the right materials, or when we get within the Glen Elg the Glen Elg area, we may choose to do it there. But that's after this rock that we're at. That's sort of our next target that we've got planned for right now.
Yeah, I might add a little bit on that as well. That the scooping activity that we hope to do, probably in a couple of weeks or so. One of the things that we need to do prior to that is to do a set of additional engineering checkouts of the scoop and the Chimera sample processing equipment. And in particular, we want to do a more or less full dry run on the spacecraft using the instruments and using the Chimera, but without having gotten a sample. Basically, just sort of an air sample, to put the arm and all of the relevant pieces of hardware through their paces. And I would imagine that's not going to happen until the end of next week or so at the earliest, at which point then we'll really be ready to start scooping. I think everybody probably knows, but if you don't, the scooping process itself also is fairly involved because it requires us passing multiple samples through multiple scoop elements through Chimera to basically make sure that it's all been cleaned out, essentially, that we're really at a point where we can take our first science sample. And so that's going to take a while as well. So the process of getting our sampling is a very involved one that we'll lay out over the next 3 weeks probably.
We're going to go now to Kelly Beatty of Sky and Telescope.
Thanks very much. This is for Richard or John, and I came in a little bit late, so if you did this already, I apologize. Can you give me just a broad brush when you expect to get to Glen Elg and some sense of how long you plan to stay there?
Yeah, so again, Glen Elg is not an actual point. It's an area, and it is the area that gets us access into the outcrop. So as we drive along, we're moving down a rather gentle slope, and then if you look into the distance and you see those rocks that have the darker bands in them, at that point we begin to drop in elevation more significantly. So we'll lose a couple of meters of topography, and we expect then the bedrock to be exposed in this area as we get there. When that actually begins is uncertain to us because we're looking at the same images you guys are looking at. This is currently the best that we have available, looking in the drive direction, and so it's just uncertain exactly where, given the fact that it's like looking down a staircase where the stair steps are getting steeper. You can't really see that far ahead to know exactly where we're going to get there, but I'll ballpark it and say probably in the next couple of weeks.
And again, that very much depends on if we stop along the way and do other things, right? I mean, if we stop and decide, because John's sort of charge to the science team is whenever we're not doing something else, we're driving. And so if we stop to do SAM atmospheric measurements, for example, then we're not driving. If we stop and do scooping, then we we wouldn't be driving. And so it's a little bit hard to answer the question because it depends on if we stop along the way and do other stuff.
That's okay. I won't hold you to it. Thank you.
Okay.
All right, we're going to go now to Todd Halverson with Florida Today.
Thank you very much. I was wondering if Richard or somebody could tell us a little bit about Jake, whether he had wife, kids, and what happened. It sounds like a very poignant story, and what his role was in the Sojourner Spirit and Opportunity missions, and I have a follow.
Sure. Yeah. No, I will give you a brief overview. He was single. He does have a family, I think, that lives in Ohio, brother and some family, and so he does have an extended family there, but no direct family here. He was actually a mathematician to begin with, and I think there's something out there called Rob Manning was telling me there's something called the Matveev theorem, which is some super obscure sort of mathematical theorem that you can Google that Jake was responsible for. And then he came here and worked as one of the original technology developers of the six-wheel Rover, the Rocky 7, the things that were really in the first days of thinking about flying mini rovers or micro rovers on the surface of Mars. And he was actually basically the guy who was a system engineer in charge of the Sojourner design. He worked closely with Donna Shirley. For those of you who remember her, she was the lead of the Sojourner rover, and he was the one that was in the position of being kind of the guy that had to tie together all of these, the disparate elements, mechanical. The avionics, where all of it was being done, for those of you who remember, for a very, very limited amount of money, and Jake was the guy that kind of had to come up with the overall system design for Sojourner. After Donna went off to be the Mars program manager back then, he actually ran the Sojourner team for probably the last couple of years and was in charge of its operations on the surface when we got there with Pathfinder. After that, he transitioned to MER pretty early on in the project and was kind of really the guy responsible for system engineering, the overall rover design, and in particular, thinking about how mobility would be used, how we would essentially picking up from what we did on Sojourner, how we would take this much larger rover and make use of it on the surface. And he actually stayed on the project quite a long time after landing. He was actually he was sort of in charge of all of the spacecraft operations for Spirit and Opportunity for probably 5 or 6 years after landing. It was only really relatively late in the process where he came over to MSL, and again with the idea of helping with surface operations, focusing on rover, being the rover sort of operations chief engineer. So yeah, he's had definitely a big impact, not only on the success of those missions, but on the folks that worked on the team. Really is probably one of the top 1 or 2 experts on surface operations here at JPL.
And Richard, if I could just add one personal story, my own experience with Jake, that the Spirit and Opportunity, I remember that as the months rolled by and it became clear that the rovers were going to last longer than their warranty, the team sort of started up a fun sort of casual guessing game or pool about how long they would go for. And I will never forget the moment when Jake walked into the room and somebody asked Jake what his prediction was. And we were all guessing months and maybe a year at the most. And each year we would revisit this and people would go for another year. Jake, I believe, actually said that if this rover lasts 6 months, it'll probably last 6 years. Seems to have been pretty close.
Okay.
Jane, thanks. And if I could have a follow, I was wondering when you put the contact instruments on this rock, what are you going to be able to learn as a result of those operations? And I was wondering if anybody could take a guess on how this interesting rock got on this barren, flat plane, whether it got burst out of a volcano or how did it get where it's at? Thanks.
Real quickly, the measurements that we're going to make involve an assessment of the chemical content of the rock. So the APXS is an instrument that flew on Pathfinder. It flew on both Mars Exploration Rover, Spirit and Opportunity, and now it's here on Curiosity. And so this is our kind of tried and true workhorse. It's just this time around it's a little bit smaller. It needs less time to get as accurate a measurement as we could do on MER, and so that means it's more nimble in its activity. And ChemCam is the remote sensing tool that we use, this laser, which is a new technology. It has not flown before in space. It's making measurements. We can look qualitatively at those measurements and see that they are detecting silicate minerals where we deposited. The team has already released that information, and so the point is that here we get to really test a comparison between something which is tried and true with kind of the latest and greatest new technology. So that's sort of the simple answer for that. In terms of how this rock gets here, this is the kind of rock that we see all over the surface of Mars wherever we land. There's chunks of dark-looking rock that are lying around. We don't know in particular what this one is, but our sort of general consensus view is that these are pieces of secondary impact ejecta from an impact somewhere else, maybe outside a Gale crater, that throws a rock onto the plains here, and it just goes on to sit there for a long period of time on the surface, and it just weathers more slowly than the stuff that's around it. So that means it's probably a harder rock.
Okay, we're going to take a question now from Leonard David at AIAA Aerospace America.
Hi, thanks. I guess for Richard, I've kind of lost track of whether you folks have been able to reassemble the entry, descent, and landing, and how Medley worked, and what kind of data came out from that particular those sensors.
Yeah, we probably can talk about it in more detail at a subsequent event, but basically the EDL reconstruction team has gotten going in earnest. I think you guys might have recalled from around the time of landing that Adam Stelzner was about to have a baby. He and his wife were about to have a child, which that did in fact occur. And so he's been off doing that for a couple of weeks, but he's back now, and so he's got the team working on doing the reconstruction. Some of that work has been, there have been some preliminary results that have been identified, and I mean the system generally worked as well as or better than predicted. But they are definitely starting to come up with numbers as to exactly how much recession did they get in the heat shield and things like that. And so that there is a big effort in place that the Mars program here is funding to do a full EDL reconstruction and write a formal report as a result of that will take a few months, and it's started up and is going well.
Okay, and just a quick one for Mark. Just to follow up on Phobos, because it is interesting about the tidal forces. And you might say that, when is Phobos going to, you said crash into Mars. I mean, I've heard other people talk about it breaking up into a huge ring. Any speculation there?
Yeah, I'll just say the general information that I have is it will work its way in. At some point it gets so close that tidal forces from Mars will very likely break it up before it does start grazing the atmosphere and come down. So Mars may briefly have a ring system. And as far as I know, this is around 10 to 15 million years in the future.
Okay, so I can sleep tonight.
Yes, you can. And Curiosity will be safe for a little while.
Thanks.
All right, thank you. The next question is BBC News London and Jonathan Amos.
Jane, thanks very much indeed. Just a couple of quick questions. Can you give us some sort of sense of timing, how long it takes to do the tests that we're about to see? I know John said that the APXS has been used before, but I think that the one on Curiosity works a bit quicker than previous instruments. And just looking towards Glen Elg, it looks kind of bumpy ahead. So I'm just wondering what the engineers are expecting in terms of driving conditions?
So the measurement itself with APXS occurs quickly. They can even do one in as short an integration time as 15 minutes. And what the test shows on the calibration target that we did, a week or two ago, shows that this can also be done in the heat of the day, which was not something that we were really able to do very well on MER. So at the end of the day, the rate limiting step is the arm motion. Again, remember that our turret on MSL is the size of a trash can lid, and there's a lot of hardware and a lot of other instruments on there. So there's just as much planning involved to make sure that our keep out zones are not violated and that we don't accidentally graze the mast and things like that. So that's really what takes the lion's share of time to plan for. And in terms of the terrain, this is exciting for us as scientists because we can look down with HiRISE and see that there's going to be a stair-step-like sort of terrain to work with. We think that these, and we can also see in the HiRISE data that we can detour around that and kind of contour our way down into the lower reaches where we hope to do the bulk of our investigation at that Glen Elg region. So it's to be determined, and as we drive along, we'll get closer, we'll look more clearly, and we have all the tools we need to get into this exciting area.
But how long do you think the tests will take, the three instruments that you're going to use in the next few days? How many days will it take to do those tests on the rock before you can move on?
Okay, so tomorrow's a restricted sol, and we do other things that are not related to the rock. Then the day after, we will bump up, sort of approach it within a meter and a half, something like that, get it in the work volume, and then the sol after that, we should be able to do the APXS, the MOLI imaging of it, and maybe the ChemCam. So that would mean it would be a minimum of 2 days, and it would be 3 days if we in fact need to move back and in order to do the ChemCam imaging. So I would say at least 2 days, no more than 3 or 4.
Okay, I'm going to take a couple of follow-up questions, and if anybody does have a question, I'll do sort of a last call. So if you have a question, press star 1, and we'll put you in the queue. But right now, we'll go back to Seth Bornstein of Associated Press.
Yes, thank you. About Jake the Rock, in terms, I think it was John who said this is like a lot of the other rocks. Is there anything at all unusual about this? I mean, or is this just, a good first test? And the other thing I wanted to check, with ChemCam, you're saying that's, more qualitative. In other words, is it fair to say that APXS tells you what's in the rocks and sort of ChemCam tells you what proportion the stuff you just found is in it, or sort of the recipe of the rock?
Yeah, so the reason, beginning with the first part of the question, we as a science team, since we agreed to start driving, we've always wanted a rock type that we feel familiar with on Mars, something that looks like we've done it before. And these chunks of dark-looking, angular-shaped rocks that are lying out on the plains are prime candidates simply because, that's what we saw with Viking, it's what we saw with Pathfinder, we had them all over the place at the Spirit landing site, and when we analyzed them, they all turn out to have what's known as a basaltic composition. And so again, remembering that basalt is the calibration target for APXS, this is kind of a hypothesis that we have about the rock. If it looks dark, it might have basaltic composition. No guarantees on that. We're going to find out in a couple of days what this thing is actually made of. But that's the rationale for how the science team goes about thinking about what would make a good first target to do calibration on. So ironically, there are some bedrock outcrops around us, but we see this dark rock, and it seems like something good to get started on with regard to that goes. And now I've actually forgotten the second part of the question.
In terms of now, I think I may have even done it. If this is the normal type rock, in terms of the ChemCam, does that tell you more? You said it was qualitative. Does that tell you more of the amounts of the different chemicals in it, or what do you mean by qualitative?
Yeah, so the distinction there is that ChemCam is a remote sensing tool, and the reason that we put this on the spacecraft was that as we drive around, of course, we take the images, which give us a sense of what the terrain looks like from the point of view of human vision looking at the surface of another planet. But we also would like to have compositional information on the things that we can't see with our eyes. So ChemCam works in a way that gives us an approximate sense of what the rock's made out of. Is the rock dominated by silicon? Is the rock dominated by sulfur? Is the rock dominated by carbonate? So what it's really designed to do best is to drive around and tell us when we found something that looks very different from what we've got as the norm. Where APXS comes in is an instrument that you put down that will then actually give you a much more accurate sense of the abundances of the elements that make up the rock. So it's not that it's got a lot of silica, it's that it's got 56 to 58% silica, that kind of a thing.
Okay, we're going to take another question now, and this is from Lisa Grossman at New Scientist.
Hi, this is from Mark. I was wondering, you mentioned that the data from the Phobos eclipses will eventually be made available to people outside the rover team so that they can analyze it and figure out what the tidal forces are. I was wondering how long it'll take for that, for the data to be made available to other people, and if you had any other resources or people I should talk to if I wanted to follow up on how that, taking these pictures and turning them into data on the Martian interior works.
Well, I'll say that the images are subject to the normal policies for this mission, which means that after some period of time, around 6 months, the data become public and anyone can access them. There may be some push to bring someone in earlier to get a head start, but the project has not approved that. But I think it's safe to say that in something not much more than 6 months, people will be able to start doing their thing with this data. And I don't want to point to people outside the team who are not ready for such a thing right now, but one of the people on the team who's been working closely to coordinate this activity is Jim Bell at Arizona State University.
Great. Thank you.
Okay, we've got a couple more questions. I'm going to go to space.com and Mike Wallace.
Oh, yeah, hi. So the Alba drives thus far have been about 30 meters or so. I was just wondering if you guys are soon going to open Curiosity up and let her go about 100 meters or so anytime, soon on the surface?
Not too soon. This is Richard. Not too soon. We're still going through and checking out the various modes of the mobility software. And so the next thing that we'll do is the so-called guarded mode, where basically not just a blind drive, but we actually use some of the onboard autonomy to basically allow us to go beyond the part that we can see with high confidence in the images, which will allow us to go up to maybe 50 meters. But some of the advanced capability like AutoNav and Visodom and some of those other things that are coming, there's still testing that's going on here on the Earth, actually, in the vehicle test bed we have, as well as we want to sort of try out those capabilities. I doubt, given how relatively close Glen Elg is, that we will use much of that, probably until we leave Glen Elg and go off towards Mount Sharp.
Thank you.
All right, we're going to go back to a couple of follow-up questions. Emily Luchtawala of Planetary Society.
Just a quick question. With MER PanCam, the resolution was too low to see sunspots on the sun. Can you see sunspots with MSL's cameras?
To some extent, we are trying to figure that out experimentally. I believe that right now we do not have a large sunspot group in there to see if we can see that, but that's something we'll be watching over time. You're seeing the best M100 images that we have on the ground so far, and I'm not picking out anything in them that I would say is a sunspot for sure, but I think we'll have some opportunities to see some larger things over time.
All right, we're going to go back now to Leonard David of Aerospace America.
Yeah, thanks. For John, I don't want to make it sound like a trick question, but it's every once in a while you get the emails from people, if we could put John on there, sky crane him down with his backpack full of tools, would you be on top of Mount Sharp right now, or how do you contrast the human capability with the mobility of Curiosity?
Well, it's a great question, David. I don't know honestly the answer to that because we as a team we're sort of largely completing construction of a geological map based on observations from orbit and quite a fine degree of granularity. And I think that as a human, the decision would be unchanged given where we landed and the capability of that map. Not our eyes on the ground, but the map that we see above. I would still go to Glenelg and look around there. It's obviously a key terrain where several things come together. And then the question is, what do you do after that? You collect a couple of samples, throw them in your backpack, and then do you head up the mountain? It might be that you trek over to the sand dunes first and take a look at that, or you go closer to the alluvial fan because you can get there. And so I rather suspect that as a human being with many more options available, you'd probably spend more time than we will be willing to give to the landing ellipse to check a bunch of things out before you'd actually try to climb up the mountain. Given the capability of the robot, we have to do sort of a triage on that schedule and very much follow what the predictions are of our geological map, and also what the rover's capabilities are, to fold in what Richard was just saying. When can we start doing the 100-meter drives? Is there a chance to use the Mastcam 100s to increase our capability to go even further? What does the terrain look like in detail when you're actually down on the ground, and so on and so forth? It then becomes a very unearth-like optimization problem in terms of the absolute rates that you achieve, but it's the same problem that you would go through as an individual saying, do I have enough water, or do I need to go back to the car and refill my water bottle before I go up there? So we're always doing the optimization. There's always a compromise in terms of how far you go versus the geology you achieve.
Thanks a lot.
Okay, that wraps up today's telecon. We've had some good questions, some good answers. So thank you, Richard, John, and Mark. And a reminder that the telecon will be archived for 1 week, and it should be up in about an hour from now, by calling a toll-free number 866-463-2179. The international number would be 203-369-1376. And, of course, lots of info on the Curiosity rovers online 24/7 at www.nasa.gov/Mars. Thanks for joining us today. Have a great day, everybody.